Okay, one more thing, a strategy that's super important. This is the fastest method to solve an equation that has fractions. Okay, so if you must solve an equation, not an expression, okay, this is for equations only, and in that equation you see one or more fractions, then find the LCD of the fractions, then multiply both sides of the equation by the LCD. You, and then if either the original left or right side had several terms, distribute the LCD. So why does this work? Well, the thing that happens is after distributing, each term gets multiplied by the LCD. That's what distributing will do. Each term has that multiplication. And the LCD is just the right thing that's going to create all the cancellations we need in each fraction. And then after that, you'll have no more fractions. There'll be no more denominators. So this seems like a lot, but you'll be good. I mean, this seems like a lot of things to remember for this strategy. So how do you remember this entire strategy? You remember the key thing. The key thing is you've got to multiply both sides by the LCD. So remember that. Remember step 2, multiply both sides by the LCD, and then the whole strategy works out. So let's see some examples. This is an equation. Look, there's an equal sign right there. This is an equation with fractions. So let's apply the strategy. The denominators here are 6, 3, and 4, and the LCD is 12. So I'm going to multiply both sides by 12. And what's really key is you have to have parentheses on the left side. On the right side, the parentheses are technically around the 3x over 4 here. They're technically parentheses, but they're hidden, and they weren't, not writing the parentheses didn't cause any problems, so I just chose not to. I chose to be lazy on the right side. But on the left side, if you don't have parentheses, what you've written is technically incorrect. Okay, it's because of the order of operations, right? We want this to say 12 times whatever was originally on the left side before. So we wrap this in parentheses. Okay, so 12 times quantity x over 6 plus 2 over 3. Now, following the strategy, on a side that had multiple terms, we should distribute. So I'm going to distribute this 12. I've used colors to try to help over here. We're going to use the distributive law. A is 12, B is the first fraction, C is the second fraction. Let's just for now leave the right side alone. So when you distribute, the left side, which looks like this, turns into AB plus AC. So we have 12 times x over 6 plus 12 times 2 over 3. And the right side, like I said, just left alone. And now I'd like to make each thing a fraction because it's really awkward to multiply a non-fraction with a fraction. So let's call that 12 a 12 over 1. Same deal right there. So in all places where there was just a plain old 12, let's have a 12 over 1. Now look, we've got fraction times fraction. So let's multiply straight across. Right? So if you multiply straight across, you have 12x over 6, and then you can cancel the in that single fraction. There's a factor of 6 on top and bottom, so you have 2x. Over here, same deal. When you squish the fractions together, then the 12 and the 3 have a partial cancellation to create a 4. There's still a 2 right there. And then same deal here. I copied the 3x, but then the 12 over 4 is a 3. Take a look at what happened. Because we followed the strategy, there's no more fractions. And now simplify 4 times 2, simplify 3 times 3 as a 9. And if we subtract 2x on both sides, you have 8 equals 7x, and divide both sides by 7. So 8 over 7 is equal to x. I should comment that sometimes people hear what's going on and say, oh, I can just ignore denominators. And that is not what happened here. So what happened here was we off to the side computed the LCD, we multiplied the LCD on both sides, distributed on both sides distributed on any side that we needed to. So all of the steps we followed were valid algebra steps. We either did the same thing to both sides or we distributed. Eventually, what happened following this strategy is ultimately by doing good habits, we got to a place where there were no more denominators. This is not the same message as just ignoring denominators. Okay, so multiplying both sides by the LCD eventually led to 2x plus 8 equals 9x. That, which, by the way, of course, has no fractions. This is different from ignoring denominators. Here's what happens if you ignore denominators. Up here at the top, people will sometimes hear the message incorrectly as if you just erase the 6, the 3, and the 4. If you do that, you'll be left with x plus 2 equals 3x. That's not correct. If you look at that equation and you try to solve this equation, you're not going to get 8/7 as the final answer. Give it a try. So please don't hear the message as being ignore denominators, because that was never the message. The message here is compute the LCD and multiply by both sides, because if you do that and then follow the fraction habits and distributing and all that, eventually you will get no more fractions. Here's another example. Ignoring denominators, by the way, would just lead to 7 equals 2 minus x. That's incorrect. Okay. Um, because we actually have here, again, an equation with fractions, the strategy is compute the LCD. The LCD of 10 and 6 happens to be 30, so multiply both sides by 30. The right side had 2 terms, so that must be in parentheses. The left side of 7/10 we could have put in parentheses, but out of laziness we didn't. On the right side, with the multiple terms, that was required. Now, because there are those parentheses, we can rewrite the right side using the distributive law. So distribute 30, you have 60 minus 30 times x over 6. Think about how it would be less awkward to turn many of these things um, into fractions instead. So the 30 here is 30 over 1. And then this way we can, create our cancellations. The factor of 6 on top and bottom have canceled. Factor of 10 on top and bottom here. So 30 over 10 became a 3. And that now, since all of our denominators are over 1s, we can get rid of those. We have 21 equals 60 minus 5x. Here, I chose to add 5x to both sides and subtract 21 on both sides. That led to 5x equals 39. Divide both sides by 5. Okay, you might eventually be comfortable not writing this second line, third line, and fourth line. So you might directly jump from this first line of the answer directly to 21 equals 60 minus 5x. If you eventually feel comfortable skipping all these steps in the middle, that's okay. But I would encourage you to write them, or at least some of them, because there's a lot of confusion otherwise. So for me, I want to show you the detail because I don't want anybody to get lost by not showing the detail. Okay, here's another method. Sometimes students like this method. I think this method takes more time. Get all the fractions on one side and write that as a single fraction. So if you add x over 6 to both sides, you get this, and now all the fractions are on one side. So what happens here is we're not doing anything to both sides, so I just still copy the 2. It is crucial to copy the 2. Sometimes people don't do that. And then take the 2 fractions and, following much earlier concepts of just fraction stuff, create a common denominator and then stick this all together as a single fraction. You really need to keep writing the equals 2. If you don't, people will just leave their final answer as this fraction 21 plus 5x over 30. But that's not the answer. The original thing was an equation, so the final answer needs to be an equation. At this point, once you have a single fraction, you have to multiply by 30 on both sides. Keep in mind, that's what we did in the previous solution for this. So undo the divide by 30, multiply by 30 on both sides, and you have 21 plus 5x equals 60. You get 5x equals 39 as before, x equals 39 fifths. Okay, so here's the thing. I point this out to say if the question were different, if the question were just take the expression 7/10 plus x over 6, and you had to simplify, then the common denominator thing is the only approach. Though I point this out to say we have an equation though, right? The question appears to solve an equation. There are 2 sides to this equation, and it's actually faster to multiply both sides of the equation by the LCD right away. Okay, interactive question. We just solved the same equation a second way. Which way do you why do you think the first way using the strategy is faster? So I've claimed that it's faster, but why actually is it faster? So I need you to go back and compare the work for answering this both ways and see if you can, I need your sort of philosophy answer to this.